Binary class classification with one example. The difference between classification and regression is regression will try to fit best fit line through the data, and classification will distinguish two or more classes by doing a decision boundary. Okay, how it is done and all we'll see today. So the y variable here is categorical. In a classification problem, the y variable is categorical. In a regression problem, the y variable is numerical and a real number. Okay, so that is the difference. As soon as you look at the data at the problem statement, you will be able to identify whether it is a regression problem or classification problem. Accordingly, we should use algorithms. There are different algorithms for different, the regression and classification. Some algorithms will work for both regression and classification both. Okay, so we have seen, data preparation, a simple example of data preparation. So, these handwritten digits, somebody took pictures and then converted them to pixels and then labeled them as the human being knows. So, human labeling is very important. Whether an application is trying to label the data or a human being is trying to label the data, human labeling or the business logic to label is very important. So currently in the industry, the problem is labeled data is not available. For all the problems, labeled data is not available. And in future, right, we'll have it because most of the people will have AI knowledge and they know how AI works or machine learning algorithm works. The data getting dumped into database will be appropriately dumped, or while the applications are working, they'll try to create labels while storing the data. They'll try to create the labels also, appropriate labels also. That way, you'll have huge volumes of data at for any problem, and building models becomes easy. Maybe some data pre-processing and cleaning activity might be there, but model building activity becomes easy. It may take time, right? Maybe 4 to 5 years it may take time. In all the industries, you will have labeled data. So that's when the AI is going to become too popular. Now it is popular. Even now there are openings and people are not available to occupy those positions, but in future, right, we'll have more positions because data is going to be available. Labeled data is going to be available. Okay, so I hope you got the point. Any questions there? Okay. And now we have taken that min data set and then converted it into a binary problem because we are trying to understand binary class classification. Okay. So I converted to 5 not 5s. You can do like 1s not 1s or 2s not 2s, 0s not 2 zeros, whatever. And then we built a model, built a logistic regression model using SGD classifier, stochastic gradient descent classifier we have used. There is an algorithm called as um, um, logistic regression. We can use that also. Logistic regression in linear models. Logistic regression is there. You can use that algorithm also. But I used SGD regressor because SGD classifier because we know the algorithm, how the algorithm works, and that is actually the basis for deep learning. And our focus is to learn, to learn deep learning, very extensively. So we did all the steps similar to regression. We splitted data, but here we used train test split because it uses stratified split. And then I took one record and tried to show how the pixels are being formed when you convert a picture into a pixels, how it is actually getting converted to show you. This is a simple example. On a color picture, right, you cannot see that. Like maybe 3 channels, maybe you'll have 3 different numbers, and it will be a bit difficult to visualize there. Okay, and then I converted the target variable into ones and zeros, and I intentionally gave the minority class, right, the 5 records 1 and not 5 records 0, because if you don't do that, the accuracy metrics like confusion matrix, precision recall, and F1 score also mislead you. This data set, when we converted it into a binary problem, we had a imbalanced data set. Right? On the 5 class, we have 3,700 records, and on the not 5, 38,000 records. So it's an imbalanced data set. So we gave 1 to these records, 0 to these records. If we don't give that way, like accuracy, accuracy score, precision and recall will also mislead you by showing a big number as accuracy. So we have seen that accuracy actually is looking into count of correctly predicted divided by total number of records. But confusion matrix is looking into 4 different things. And how many positives correctly predicted positively, negatives negative, and positives negative, wrongly predicted positives negative, and negatives positives. Right? So when we look into these and then calculate precision and recall, provided the minority class is given 1 and the majority class is given 0, right? The model, the accuracy looks good, right? The accuracy actually, the model's metric, the accuracy metric will show you the exact result. Okay, so yesterday we have seen that. So when we calculated precision and recall for this particular data set, we had got 93 and 76, precision 93, right? On all the positive predictions, 93% are correct. On all existing records, existing positive records, 76% are correctly predicted. So 24% of the existing records are not being predicted correctly. Okay, so that's a huge amount, right? So when you look at recall, you'll understand how many in the existing data are not being predicted. Existing positive records in the existing data are not being correctly predicted. Okay, so then we looked into F1 score. It's a harmonic mean which actually tries to bring down the score towards the one which is in precision and recall, whichever is low, it actually tries to bring down to that place. So that far we have seen yesterday, right? So when do you need high precision and when do you need high recall? This right. Sometimes we may need high precision and sometimes we may need high recall. So F1 score favors the classifier that has similar precision and recall. Right, the statement. F1 score is used when you are trying to build multiple models and decide. Sorry. So you are building a logistic regression model and then a random forest and then SVM. 3 models you built, and you wanted to decide which model to use. Right. In that case, you need to use F1 score. Because it's a 1 score, and on all the 3 models, which one is high, that one you will take, right? That we even in regression problems also we did that, right? So R square score we calculated, whichever is high, that model we actually choose. Or in a given model, maybe SGD classifier, if you are trying to run multiple iterations with different hyperparameters, you want to see which one is good, right? In that case also you need to look into F1 score. But F1 score favors that have similar precision and recall. Did you understood this statement? Anybody understood this statement? F1 score favors classifiers that have similar precision and recall. No? Yes? Maybe
both the values are close to
each other. Both the values should be close to each other. Then only, right? So if one value is low and one value is high, it is going to bring down to the low value, right? Yesterday we have seen 0.1 and a 0.9. When we tried to calculate F1 score, we got 0.18, right? So the like that. So this is not always we want, right? In some cases we want high precision, and some cases we want high recall, right? Examples are like this. High precision example.
1 second, sir.
Yeah.
You said F1 score favors classifiers. So are there multiple classifiers, or what is that it is referring to?
That's what I said, right? No, you are trying to build a logistic regression model, SVM model, and a random forest model. 3 algorithms.
Okay, one of them.
3 classifiers.
Okay.
Okay. One more thing. When you are doing k-fold cross validation on a single algorithm, you will have multiple classifiers, right? Using a single algorithm, right?
Okay.
Okay. So some cases, right, we want high precision, and some cases we want high recall. And so for some models, we expect high precision, and some models we expect high recall. So example for high recall, I have taken one. Healthy food classifier, right? Healthy food. Suppose that you are building a classifier that actually predicts whether a food is healthy or not. No, maybe we built a mobile application where you take a picture of a, of the nutrition facts, and immediately it will actually tell you whether it is good for health or not, right? So healthy food classifier. So it should have high precision, because whatever it predicts as good should be good, right? Whatever it predicts as good should be good. So high precision should be there. Recall, we don't care. Is my statement understood? Recall, we don't care. In this particular model, right, healthy food classifier model, precision should be high. So if you look at this, when I say precision should be high, this number should be 0. I don't care whether we have some number here or not. If this number is 0, what you get? Precision. If this number is 0 here, how much is the precision?
100%.
100%, right? 100%, 1, right? So if you look at this number, if you suppose that this is a healthy food classifier, if you look at this number, what is it doing? What is this count in a healthy food classifier?
Zeros.
No, what business point of view I am talking about. In a healthy food classifier, I am saying this is the count of healthy food, right? You have like, for 42,000 records or 36,000 records you passed, and 33,000 records of healthy food. Okay, healthy and non-healthy food, right? This count is what?
Correctly predicted healthy food count.
Yes, good. This is a healthy food correctly predicted one, right? This is
Correctly predicted unhealthy.
unhealthy food correctly predicted. This one,
Incorrectly predicted unhealthy food.
unhealthy food as healthy food, right? This is wrong. This should not be, our system should not be doing this, right? This one, the 702.
Like healthy food is classified as unhealthy.
Healthy food as classified as unhealthy. This is okay, right? Healthy food is classified as unhealthy. This is okay. I am saying not that the model is good. No, even if some healthy food is predicted as unhealthy, that's okay, because people are not going to take this. There is no harm for the people, right? If this number is harm, this number is not good. Why? This number is not good. Why?
Because that is unhealthy and we are saying it as unhealthy.
The model is saying it is unhealthy, and model is saying healthy. People will eat it, and then they may get sick, right? That is bad. So the application, right? The application on which you are working, and the business, the business domain, domain expertise, right? Business knowledge is very important in deciding for a model whether precision is needed or recall is needed. High precision is needed or high recall is needed. Understood the importance of business and the which score should be taken into consideration in which scenario? Any questions there? Any questions? Understood? Should I explain again? If you don't talk right, I might be like, no, I don't know whether you know it or not. Whether you got it or not. Got it?
Yeah, understood.
Okay. I think you got it, but rest.
Yes, sir. Understood.
Okay. So that's the importance thing. So if you get 0 here, if the model is you built a model that actually gives that actually predicts not healthy food as healthy 0, right? That is the expected model, right? So and the other thing is high recall. Heart attack probability classifier. Heart attack probability class. If you feed a person's blood work to the system, right, the numbers to the system, it may be predicting, whether the person is susceptible to get heart attack or not. Okay, heart attack probability classifier. Here we need high recall. If you look at this table again, suppose that you passed 33,000 records. I am saying for a heart attack prediction thing, high recall is needed. So I am expecting 0 here. Even if there are some numbers here, that's okay, I am saying. Why? Because not a heart attack possible candidate and heart attack possible candidate. Positive case is heart attack possible candidate. And negative case is not a heart attack possible candidate, right? So even if you are predicting some not heart attack candidate probable candidate as a heart attack probable candidate, that's okay, because the people will actually do some exercises and they'll become more cautious, right? But if some heart attack probable candidate is predicted as not, that is dangerous. That guy will actually do all mischievous things and he may get into trouble, right? So the system should work, high precision, high recall should be there. When we are trying to build models like these, depending on the business scenario, you should be deciding whether we need high precision or high recall. Okay, so we understood the F1 scores importance and where we need high precision, high recall. But there is a question, right? When we built a model, we got some number of precision and some number high recall. Can we tweak these, or can we make the model get the expected precision and recall? That's the question. Okay, I'm going to answer that question. So far, are we good? Some models expect some business scenarios expect high precision, some business scenarios expect high recall. The business user may come and say, right, I don't care, I don't care, I care more about the prediction. The prediction should be correct. The positive prediction should be correct. That means precision should be high. No? So the other way around, I cannot make a statement right now on that. So high recall is needed. So far you're good, right? So far we are good, right?
Yes, sir.
Okay. So now, right, how to play with this, precision and recall. So let me show you something here. So we got some precision and some recall, right? And yeah, some F1 score. So there is a method called as predict proba, okay, which will actually give you probabilities of the class. So let me try to run all above once. Okay. So now, right, there are two methods called as predict proba and decision function. Okay. What is decision function? What is probability? We'll talk about probability in a moment. But there are two classes in the data set, right? One is fives, other is not fives. So it is going to give probability for fives and not fives both. Okay, whichever is high, the record belongs to that particular class. Okay, predict proba method will give you probabilities of each record. Right? Each record will have two probabilities, one for the positive class and another for negative class. If you look at these two numbers, if you look at those two numbers, right? So, can you tell me which class it belongs to? Can you tell me which class it belongs to, this record? Did you understood this? Whatever I am showing right now, this table.
Yes, sir.
So can you tell me which class the record belongs to?
The first number corresponding class.
Which one? What is the first number corresponding class? Classes underscore will give you, right? Classes underscore will give you the order, right, in which the classes are considered. So this record belongs to 0, right? This record also belongs to 0. This record also belongs to 0. Not 5. Not 5 records. These are all. So, do we have any 5 records? No, all are not 5 records only, because most of them are not 5 records, right? That's where we are seeing those. So there are dots means, right? There are many other things. So classes underscore is a attribute that gives you the order of the classes. So this is 0, this is 1. So the record belongs to 0 because high probability is there in the 0 column. Okay, that is predict proba. Right? When you say predict, it is going to predict the class. When you say predict proba, it's going to show you the probabilities. When you say decision function, it's going to give you decision scores. Okay, so how is this probability calculated? I'll explain in a moment. But what is this decision score? Decision score is the distance between the decision boundary and the class. Okay, the record, sorry. The decision boundary and the record, there will be distance, right? So if it is close, the decision score is going to be low. If it is far, the decision score is going to be high. So using decision score or probability, we can actually play with the precision and recall, whatever, right? Precision and recall scores. So I'm going to show you how to play with the precision, the decision scores and probabilities. Before we understand how to play with, right, we need to understand the logistic regression algorithm. Okay, so the same way, like there are x1, x2, and so on, xn and y. Right here on the classification problem, the y variable is going to be categorical. Okay, and then it when you pass it to the logistic regression, it uses a hypothesis function called a sigmoid function. Okay, this is a sigmoid function, 1 by 1 plus e power minus of theta 0 plus theta 1 x1 plus theta 2. This is a linear equation, right? So in the linear regression, this was the hypothesis function, but in logistic regression, 1 by 1 plus e power whatever is the hypothesis function. Why this hypothesis function we'll understand in a moment, because we'll understand in a moment. So when you pass your train data, the model will understand and find out these thetas here. Okay, in this 1 by 1 plus e power minus whatever, right? In this equation, these thetas will be found out when you pass the data. So when your new record is passed, right, the access will be substituted there, and then the prediction will be made. So I'll show how the prediction is made and all that. Okay. So the logistic function, the hypothesis function for the logistic regression algorithm is h of x is equal to g of in a linear regression, right? It is just that equation, but in logistic regression, it's a function of that equation. Okay, so function of that equation. What is that function? 1 by 1 plus e power minus z, where z is the linear equation. So logistic regression gives you an output between 0 and 1. It is always between 0 and 1. Well, will never be 0, will never be 1. Okay. So when the hypothesis function is giving you a number between 0 and 1, the number which is outputted is the probability. You look at this, right? This number or this number is calculated by this function, this hypothesis function. Okay, that number is nothing but the probability. Okay, got it? Any questions?
One question, sir. So probability for what? I'm missing it.
Probability to say the record belongs to either 0 or 1.
Okay. In our example, like
Your
not
question,
5 and 5.
your question, I got it. Probability to say the record belongs to 1. Sorry, that's the record. No, if the probability is 0.9, that means the record belongs to 1. The probability is 9.1. The record belongs to 0, not 1.
Okay.
Right? That's clear, right?
Yeah. Thanks.
So the number calculated here, based on that, it will give you only one number, but the algorithm will calculate the second number. Okay. So the logistic regression algorithm gives you an output between 0 and 1. That is taken as probability, and using the probability, we can make predictions. If the outcome of this sigmoid function is greater than 0.05, so greater than 0.5, we say the record belongs to 1. If it is less than or equal to 0.5, then we say the record belongs to 0. Okay, so I think greater than or equal to 0, 1. So the shape of this function, logistic regression function, is going to be like this. On x-axis I have taken z. On y-axis I have taken g of z. That means what? On x-axis I have taken the linear equation. Okay. On y-axis I have taken the hypothesis function. What is the hypothesis function? 1 by 1 plus e power minus z. When you substitute the z value into the equation, how the the shape is actually getting formed. Okay. Understanding this curve is important, because if you look at this z value, right? If the z value is less than 0, what is z value? Can anybody tell me? What is z value? Z value?
G-score?
No.
Linear
Multiple of
equation.
Function.
Linear equation, right?
Okay. Yeah.
See, yeah, that's I suspected that you are going in a wrong direction. So you see this. In a linear regression, what we are doing? We are passing a train data to the algorithm, and it is finding the thetas, right? It is finding the thetas and the linear equation, right?
Yeah.
In here also it is finding thetas only. But in this equation it is finding 1 by 1 plus e power minus of that linear equation. Okay? Okay, got it?
Yes.
So here the important thing is that linear equation only. We are not using the linear equation's outcome directly, but we are substituting that into this equation. I'll tell you in a moment why we are substituting that into that equation. Okay, sigmoid function, why we are using in a moment, I'll tell you. But this equation is very important, and we denoted that equation with z. That's it. It is not g-score. This linear equation, once after knowing thetas, the linear equation is denoted with z. Suppose that for a particular record, the z value is less than 0. That means what? The linear equation's outcome is negative. Okay? If the linear equation's outcome is negative, what is happening to the hypothesis function? That's what we are going to observe now, right? So if the linear equation's outcome is negative, I have taken an example value minus 10. Okay? Linear equation's outcome is minus 10. Right? So when I substituted that minus 10 into this logistic function, 1 by 1 plus e power minus of minus 10, 1 by 1 plus e power minus 10 we got. E is 2.34 something, 37 something. Value of E. Two point, no, 2.718 whatever, right? So 1 by 1 plus 2 power 10, is it going to be less than 0.5 or greater than 0.5? 1 by 1 plus 2 power 10, is it going to be less than 0.5 or greater than 0.5?
Less than
Obviously
0.5.
Less
less.
than only.
Less than only, right? So if you look at that g value, if the linear equation's value is less than 0, you are getting a number less than 0.5. Do you agree? Whether you put a minus 1 or minus 10 or minus 100 or minus million in the g value in this logistic function, you will get a value less than 0.5. Do you agree with that statement?
Yes, sir.
Yes.
Right? If the g value is greater than 0, greater than or equal to 0, even if it is 0, right? G is equal to 0 or greater than 0. I have taken 99, an example. I am substituting that. See this, e power 99 divided by e power 99 plus 1. Is this going to be greater than 0.5?
Yes.
If z is equal to 0, right, what's going to be the value? 1 by 1 plus e power minus 0. It's going to be 1 by 1 plus 1, right? 1 by 2 is equal to 0.5. So if the z value is greater than or equal to 0, the sigmoid function value is going to be greater than or equal to 0.5. Okay. So linear equation, we can use linear equation to predict classification also. Okay, to do a classification model, we can use linear equation also. If the value is less than 0, we can say the record belongs to 0. If the value is greater than or equal to 0, we can say the record belongs to 1. But instead of doing that, we have taken the sigmoid function to do that job for us, right? Do that task for us, right? So that you will get some probability there, and it will be easier for us to do more, So when you look at cost function and all, right, you will understand better. If you use linear equation, it may not be that convenient. So if you use the sigmoid function, it will be convenient for us to mathematically formulate the thing and find out the best theta values. That's where we are using sigmoid function. Got it? Sigmoid function is actually using linear equation to generate the probability. And when the linear equation's outcome is less than 0, it is generating a probability less than 0.5. And when the linear equation's outcome is greater than or equal to 0, it is generating a probability greater than 0.5. Okay? Got it? Got it? Any questions? No? No questions? You must have one question, at least. No questions, I'll ask a question then. Right? So how is it how is it actually generating the probability? Right? How is it actually generating the that number, right? While doing the training, while we are actually training the model, what is our goal?
Prediction.
What is the goal of the model?
Prediction.
Sorry.
Prediction.
Prediction, right? So why this equation? Still we should have that question. When you are trying to predict, what you are trying to predict in a binary class classification, what are the values you are trying to predict?
Either 0 or 1.
Yes, right. So if you take the hypothesis function, this logistic regression, that sigmoid function, the value given by this sigmoid function is going to be between 0 and 1. And your outcome is, the classes in the target variable are 0 and 1. The algorithm will try to generate a number close to 0 if the record belongs to 0. Right? If the record belongs to 1, right, this sigmoid function will try to generate a number which is close to 1. That way, the algorithm will try to converge towards the target value of each record. Got it? Got it? Got it? Yes, no? The point I am trying to make is we can use the linear equation also to make prediction on a classification problem, but the linear equation will give you big numbers. It is not going to give small numbers like 0 and 1. It may give, but it will not be that convenient or comfortable. The algorithm will actually strive a lot to reach to that place and it may not reach, right? And the other point is it is trying to distinguish, right? Decision boundary we are trying to do, right? So this equation this equation will generate a number which is which is between 0 and 1. The target values are actually 0 and 1. So the algorithm will try to generate a number close to 0 for the record which is 0. For the record, the y value is 0. And it will try to generate a number close to 1 for the record which is 1. When I say it will try to generate a number close to 0, number close to 1, it is trying to find these thetas in such a way that the logistic function will generate a number which is close to 0 and close to 1. Got it? Ultimately, where am I coming? Where am I coming? The weights of the equation are the outcome of the algorithm. Got it? Did I confuse you? Clear? Everything clear?
The one question, sir. Can you please go to the previous slide? Yeah, here for theta 0, theta 1, theta 2, all those things. See, we arrive at those things by keeping something in y. For us, y means either 0 or 1. Is that correct statement?
Yes, Andy.
Okay. So when I have 1000 records, then I'll try to find this theta 0, theta 1, all those things such a way that it matches the corresponding y's. That is nothing but class 0 or class 1.
Yes, Andy. Yes, Andy.
Once we arrive at these thetas that way, then we try to predict the probability, and once the probability arrives, then I'll predict that record belongs to either, if probability is close to 1, I'll say y, its corresponding new y, predicted y is 1, otherwise I is predicted y as 0.
0. Yes.
Is that the right
Yes,
understanding?
sir. Everything is correct. Your understanding is exactly correct. Why we took the sigmoid function? I tried to answer. Sigmoid function is convenient in generating a number which is close to 0 and close to 1. Your understanding is correct.
Sir.
Yeah.
It is a stochastic gradient descent, right? Even it is logistic regression. So in a similar way, it also tries to take some thetas and converge.
Yes.
When it will actually stop. So
here also we'll take a cost function which is convex. When the cost function is convex, right? The bottom of the pit, right? At the bottom of the pit, the slope is going to be 0. Here also we'll take the tangent slope only. The same equation, theta is equal to theta minus alpha into derivative of the cost function. When the derivative of the cost function reaches close to 0, we'll stop. Or is 0, we'll stop. Got it?
You mean we're taking the same cost function?
No, that I'll explain in a moment. Same cost function will not work. We'll take log loss here. Okay. So this part is clear, right? How the sigmoid function is predicting and how exactly it is learning. We know that. So now the threshold, right? 0.5 threshold is the default threshold. So when I say 0.5 threshold is the default threshold, the algorithm will try to see all the probabilities, all the sigmoid functions outcomes which are less than 0.5 and says it is 0 record. The prediction is going to be 0. For all the records which is greater than or equal to 0.5, it says the record belongs to 1. Okay, 0.5 is the threshold. Now I have a question. Here I showed you probabilities, right? These are 0 probabilities and these are 1 probabilities, right? If I take probabilities and change the threshold, can I change precision recall scores or confusion matrix structure? The numbers in this confusion matrix, can I alter if I change the threshold? Can I? Suppose that I said 0. Less than 0.4, all 0 records. Greater than or equal to 0.54, all positive records. Can I change the counts here in that way?
Yeah,
I think so.
Yes, right. Yes, I'll show you that in a moment. We can do that, right? That is the way to play with precision and recall. If a model expects more precision, we'll try to take the probabilities and play with it and change the predictions. Let me show you. Let me show you that whole thing clearly. And I'm trying to give you some intuition there, and then I'll show you the clear example, a simple example, and then we'll move on to our code example also. This is very important. In real time, this is what you do. Building a model, anybody can do. A kid can do, right? You give cleaned data. Building a model will take 20 seconds. But before the model building and after building model is the major activity. So we are trying to understand those mechanics here. So if you look at this particular example, right, there are 0 records and 1 records. There is a decision boundary, right? The decision boundaries equation is -3 plus x1 plus x2. If you substitute x1 and x2 random values, right, 0, x1 and 3 x2, you will get a point here, and x2 0 and x1 3, you will get a point here, right? So x2 3 and x1 0, okay, you will get a point here. So all these dots, if you substitute different data, different ones and twos and all that, right, you will get dots, and this is the decision boundary. So when you sigmoid function generates a number close to the target value. If the target value is 1, whatever I explained right now, the target value is 1, h of x is going to be close to 1. If value is 0, the h of x is going to be close to 0. We can consider this as probability of a record belonging to 1. Whatever the number, the probability given is the probability of record belonging to 1. This is another question asked by, I think, Keshwa, right? So both are there, answers are there, right? See this. So whatever, right? If you actually take a data point here and try to substitute into this equation, you will definitely get a value greater than or equal to 0. Above this line is all greater than or equal to 0. Below this line is all less than 0. Right? If you have time, right, you can actually play with this and see. Logistic regression will classify data at threshold 0.5. So we know that logistic regression is using threshold 0.5. We can play with the threshold and change the precisions and recalls and F1 scores and whatever. So let us look at that example here. So there is a data set with the triangles and circles. Okay. And I converted triangle as 1 and circle as 0. Okay. It's a balanced data set. So it doesn't matter whether you do 1 or 0 or 0 or 1. And now suppose that I built a model and the hypothesis function found these probabilities 0.6, 0.3, 0.2, like that. Okay. At default threshold, right, the prediction is happening like this. Internally, the algorithm is actually predicting like this. After taking the probabilities, it is actually doing this function h of x greater than or equal to 0.5. Some will be true, some will be false, right? Do you agree? This one is going to be true. If you put the h of x value into this equation, this is true. This is false. This is false. This is false. This is true. Right? Do you agree? 0.6 greater than greater than or equal to 0.5 is true, right? Boolean expression, right? So you can consider true as 1 and false as 0, right? Default threshold, we made 2 errors. The record belongs to 1, but the prediction made as 0. The record belongs to 1, the prediction made was 0. We can correct this by changing the threshold. If you have access to probabilities, you take probabilities. Instead of taking the algorithm.predict, you take predict proba, you take the probabilities and apply this threshold, change the threshold as 0.4. That way the errors got corrected. See this? This one became 1 and this one became 1. Got it? This is how you can play with the model and make the model's performance higher. Got it? Accuracy higher, high accuracy, high perform, good classifier you can build. Did you get it? This example is clear?
Sir, in one of the slide you put the calculation of g, the function, I think incorrectly. Can you please go to the here g you mentioned h of x equal to 1 by some
1 by 1 plus e power minus g.
Correct. What is that? Then it should be h function, right? Not the g. What can you
G
give me
of
the
z or
relation?
h of x is same. G of z we call it as, or h of x. Hypothesis function, right? We define as h of x or g of z. That's the notation it is.
Okay. Okay. So
See
there
this
is some
here?
confusion to me.
Yeah, that's confusing only.
Okay.
See this?
Okay.
H of x is equal to g of that linear equation, and g of g is equal to 1 by 1 plus. It's a notation thing, not big deal. Got
Okay,
it? Huh? That's correct only. But you have a look at it once after the class. Okay. So this part is clear, right?
It may go in a wrong direction, right? If we are
Yeah. Yeah. If we are actually not taking threshold properly, it may go in wrong direction also. But I am explaining this because for some models we need high precision. For some models we need high recall, right? So when we need high precision, what to do? Model is giving some amount of precision, but the business is, business requires more precision. What should we do? We should change the threshold to make the model give high precision. Got it? Whatever client wants, we need to do that, right? We cannot say that the algorithm is working like this and I cannot do anything more, right? Got it? So you can take probability or decision score. Decision score will also be calculated by logistic regression algorithm. Decision score is nothing but the distance between each data point and the decision boundary. You can take decision score also to calculate, to actually play with the threshold, right? Play with the threshold and make predictions. Generally, algorithm takes 0 as the threshold if it is decision score. If it is probability, 0.5 as the threshold. Okay. So let me show you, in our data set, how to play with the threshold. Let me show you that. So here, right, I showed you probabilities, I showed you decision scores. Decision function is the method on the SGD classifier, right? So I have taken precision and recall scores at minus 14. For fun, I have taken a number minus 14. So see this, the predictions at a threshold, are they going to be true or false? Let me try to run these two statements. 31, 34, right? So see this? here the predictions at threshold are all trues and falses. I can take true as one, and automatically algorithm, the confusion matrix itself will accept one or true. Okay, 0 or false. See, actual y and the predicted at threshold. See, the confusion matrix changed. Confusion matrix changed. The precision and recall scores will change and F1 score will change. Got it? You take decision scores. If you want to tweak the model's precision or recall, if the model expects more precision or more recall, you can take decision scores and you take different threshold and then play with it. You know which one to take, I will show you in a moment. There is a curve which actually shows you at which point how the precision and recall scores are being acting, right? This is Seshiram's question. I'll answer it in a moment. So I randomly chose some threshold and tried to calculate precision and recall along with the confusion matrix also. See this precision became 0.95, 0.095 and recall became 0.998, right? 100% recall, right? But precision, right, out of all the positive predictions, very less, right? Even one record is also not being predicted correctly. Okay, so you got this point, right? Any questions here? Yes, no? So whatever I did on this particular sample data set, I did it on our data set. Instead of taking probability, I have taken decision score. Got it? Guys, you're all silent.
Yeah, basically it's a too much, sir, actually, because it's becoming too complex, right? So that's where maybe.
No, not complex. It is simple only, right? In the first glance, right, it looks like complex. I'll stop. In a moment I'll stop, right? Just let me show you, this far, right? This far, and then I'll stop and have a look at it today, and tomorrow we'll start with the same thing. Okay? This is very important. This is really, really very important. Okay? So I have taken different thresholds and tried to calculate precisions and recalls. And if you look at this diagram, right, at 0 threshold, this is the precision and recall we got. At this threshold, this is the precision and recall we got. At different thresholds, we are getting different threshold, different precisions and recalls. There is a function called as precision recall curve, which actually gives you precisions and recalls at different thresholds. You can actually plot it and see how the model is actually behaving at different thresholds. Okay, so at 0, this is how it is. Maybe at -5, right, you have high recall, low precision, but maybe at -2 or 3, you have kind of 90% precision and maybe around 70% recall. So you should keep an eye on both. This is called a precision recall trade-off. If one increases, right, other will decrease. If precision increases, recall will decrease. Recall increase, precision will decrease. So I'll talk about this tomorrow, and I'll stop it for today. And if you have any questions, right, you can ask.